Okay. Okay, limit as x approaches 3. First thing we try to do is see what's happening at 3. So let's evaluate the limit at 3 and see what's going on, right? We want to know if it's a real number, then we stop. If it's 0 over 0, we keep going. If it's 10 over 0, then we know it's limit doesn't exist, right? So plugging in is important. It kind of gives us an idea as to which path to follow. So let's plug 3 in. Numerator, I get 0. Denominator, I get 9 minus 6, which is 3. 3 minus 3 is 0. So this telling us that there's a hole in the graph and that the limit exists. We can go through factoring, right? That factoring method of canceling out holes in the graph. The denominator factors out to be, let's see, multiplies to be -3, adds up to be -2. So x minus 3 times x plus 1. Okay, the x minus 3's cancel out. Okay, we're left with 1. Plug 1 in for x. Sorry, plug 3 in for x, and we get 1/4. Okay. Any questions here? I want to show you that there's another option available to us. The fact that we get 0 over 0 gives us the freedom to apply L'Hopital's rule as well. So we take x minus 3, we find the derivative, we get 1. Okay, we plug 3 in for x, we get 9 minus 6 minus 3. I'm sorry, we need to find the derivative. So I don't plug in, I find the derivative. So x squared becomes 2x, negative 2x becomes minus 2. Plug 3 in, we get 6 minus 2, which is 4. So we get the same answer either way. Right. I think after learning L'Hopital's rule, it catches so many different varieties of problems that a lot of students prefer L'Hopital's rule rather than doing a specific rule for every type of limit problem. But we can't just do L'Hopital's rule whenever we want to. We got to make sure that we plug in and ensure that we're getting a 0 over 0 before we are free to apply that L'Hopital's rule.
Mr. Yang?
Yes.
Do you think like L'Hopital's rule might be like a little quicker because on the final we might like not have as much time? Because if it's like a little quicker, it'd be better to do for like that kind of problem.
Yeah, I would say I think L'Hopital's is great. And you know, you can choose obviously which method to use. So I would say that yes, in this case, L'Hopital's rule is faster. But I would also think that there are some certain situations where for complex fractions, maybe it's faster to go through common denominators rather than having to go through a messy chain rule. But yeah, I would say for this instance, yeah, L'Hopital is definitely faster.
Okay, thank you.
Yeah. So I would encourage students to use L'Hopital's rule as long as you work within their restrictions, right? We can't just jump into it without first confirming 0 over 0. So that's why it's always good to plug in first. If you plug in first, at least you know what kind of a problem you're working with. Okay, let's do another quick one here. Number 7. Limit as x approaches infinity. Let me zoom in here. When we see infinity, we have a completely different set of steps, right? And the way that we evaluate with infinity is we go and we compare degrees. Okay. And notice how x squared, these are both the same degree. So because of that, because they're the same degree, we just look at the ratio of the coefficients. So the ratio of the coefficients, because my degrees are the same, it's just going to be -1 over 4. And that's our answer. Our answer is just the ratio of the coefficients. Okay. Feel free to jump in if there's any problems that you feel like you want to do. Maybe you've looked through the packet and there's some problems that you feel like you want me to go over with you.
On the back of the first page, there's a couple like limits with trig problems. Like, could we just go over one of those? Like, kind of.
Yeah.
Thank you.
So problems like 13 and 14, we actually there are actually specific rules involving trig, but then after a couple of years, I realized, well, is it worth teaching those properties when students can just do L'Hopital's rule? And so that's really what these problems can do for us, is we can avoid learning all these very specific rules. And we know, especially, is there a need for it when we can use L'Hopital's on half of them? So let's try number 13. All right, so first thing I do, any limit problem with real numbers, I'm going to plug in. So 0, and for x, I get sine of 0 over sine of 0, which is 0 over 0. So this condition is ripe for L'Hopital's rule. So we're going to take the steps to find the derivative of these two terms separately. So sine of u becomes cosine of u times u prime, right? So cosine of u times u prime. Okay, we apply the same method for the denominator. Sine of 4x becomes cosine of 4x times 4. Now that we have a different variation of the problem, we're going to reevaluate the limit, 0 and for x, and we get cosine of 0 times 3 and cosine of 0 times 4. Okay, cosine of 0 is 1, cosine of 0 is 1, so we get 3 over 4. Okay, same idea with number 14. Okay, we plug 0 in, we get 1 minus cosine of 0 over 0. Cosine of 0 is 1, 1 minus 1 is 0, 0 over 0. L'Hopital's rule can now be applied. One goes away to 0, negative cosine of x. Cosine's derivative is negative sine. X's derivative is 1. And now we just replace our remaining expressions with our target x value. So 0 in for x. We get negative times 0. So 0. Sorry, sine of 0, which is 0. Yeah, so we see the kind of like the enormous benefits of L'Hopital's rule, right? If you see limits, a lot of times, as long as we're getting 0 over 0, we can always apply L'Hopital's rule. It can go pretty far with messy limit problems. All right, any questions with the first two pages? I'm just going to kind of highlight the steps or highlight the types of question these are dealing with. And then you can stop me and say that you want to work on it or whether you want to just pass on it. Because if you're comfortable with it, then we can move on to something else. Okay, so here's number 18. This is saying find the first derivative. And this is a problem that's going to require quotient and chain rule. Okay, do you guys want to do this one or you think you're okay?
I personally think I'm okay with this one.
Okay. All right. All right. Ishida, you can jump in if you want to see a problem done, but I'm going to just kind of go through. Cosine of x squared. This is simply going to be a chain rule problem. The squared is inside that derivative. Inside this x squared. So really, it's just negative sine of u times u prime. So I think that's pretty straightforward. This one is a chain rule. Number 20, you want to start off by rewriting the problem as sine 3x squared and then relying on outer, inner, and inside to build your derivatives. 21, same thing, chain rule, bring that 2 out, chain rule for 21. Next page. Quotient rule for 22. 23, we have implicit and a little bit of chain.
Can we go over 23, please?
23, all right, sure. Okay, we want to find the derivative. All right, so a couple of things I noticed here is the y is not separated from the equation. It's kind of inside the equation. So that tells us that we got to go through some implicit inclusion here. So implicit differentiation. There's also a little bit of a chain rule going on here, I guess, with that u prime. So we have to rely on the derivative for cosine. So cosine's derivative is negative sine of u times u prime. All right, so let's go down our derivative steps. So x's derivative is just 1. Cosine's derivative, cosine of u becomes negative sine of u times u prime. So let's go through what the derivative formula tells us to do. So negative sine of u, that's my u value. My u value is everything inside the parentheses. So negative sine of u times u prime. So u prime is asking for the derivative of this x plus y. So x's derivative is 1. Y's derivative is 1 dy dx. And the 0 is going to stay 0. So we have the derivative kind of found, but we still want to solve for dy dx. But you notice that dy dx is not free to subtract over because it's kind of stuck to the bracket, which is connected to this negative sine of x plus y. So to make it a little bit easier to kind of release that dy dx away from this connected part, is I'm going to make this negative sine of x plus y kind of distribute through the bracket first to kind of allow me to have separate terms, and then I can start moving the terms around and eventually get that dy dx by itself. Okay. If I just move this negative sine x plus y dy dx over to the right, I can just divide that sine of x plus y over, right? Okay, divide both sides by sine of x plus y. And that's as far as we can go. I know it's tempting to try to cancel these sine x plus y's out, but that 1 minus is connecting this in a way where it's difficult for us to move it. So this is as far as we can go. All right. Any questions there?
Mr. Yang?
Yeah.
I'm sorry, I know you might already pass this problem, but can we go over number 22, the one above this one? I kind of confused on it in class today.
All right, good. 22. Wait, what'd you say about your class?
Oh, I just said I got confused on the problem in class today. That's all.
Got it. You could go through quotient rule, but I think what they're trying to get you to do is to see the relationship between sine and cosecant. You see how sine is in the denominator? So really it's 1/2 times 1 over sine of 2x. And sine of u, the reciprocal of sine is just cosecant. And this is the same thing as 1/2 times cosecant of 2x. And if we start here, then the derivative is going to be a lot more manageable to see. Okay, it's the same thing.
I did
but
quotient
now-
rule today. That's why I got confused.
Got it. Yeah. I mean, if you did quotient rule, you would have gotten something that looks different than this, but then you would have been able to, if you rearrange some things, you would be able to get it to look like that. But if we start at the beginning and if we look at the answer choices and start at the beginning and say, okay, I see some cosecant here, maybe I need to get that sign in a different form, then it becomes a little bit easier. So the derivative for cosecant of u is negative cosecant of u cotangent of u times u prime. The negatives cancel out, so 2's and 1/2 and 2 cancels out. Okay, any questions with 22? All right, let me keep going down the packet here. This is implicit and product rule. This one is you just going through power rule 3 times. And then by the time you get to the third derivative, you're going to plug 4 in. This is asking for the second derivative for implicit, but we'll probably pick this up next semester. We won't do this one. (27) is kind of like a chain rule derivative. We can skip that one. 28 and 29, it looks messy, but really it's just L'Hopital's rule that can handle these. (31) mean value theorem. 32, yeah, it's kind of related. Kind of seeing if students can make the connection between mean value theorem and Rolle's theorem. Okay, 33 is Rolle's theorem. 34, implicit. 34. Yeah, this is just where you go through implicit, find the derivative, take the 2, put it in, find the x value, and then just plug the order pair into the derivative to get the slope. 35, product rule, get the derivative, plug in to get the slope, and then point slope form. (37) tangent line equation, so find the derivative, plug in the x value, get the slope, and then point slope form. 38, probably going to skip this one. This is just where vertical tangent line is set the denominator of the derivative equal to 0. There's some implicit and product going on here as well. It's a lot. (39) f prime's already given to you, so we can find the critical points, populate our first derivative sign line, and then determine increase, decrease with our arrows, and then we can look for max and mins. Okay, skip number 40. Here we can set the derivatives equal to each other and solve for k. (42), I did this in class yesterday with related rates. And then I did 43 and 40. I did problems involving the particle motion here. Okay. First derivative test. First derivative test. Concavity sign line. Second derivative test. We can skip 54. And these are chapter 5 concepts. Expand log first, and then do your u prime over u. This is quotient rule, but also involving the a to the u rule. 57, chain rule or quotient rule involving e to the u. 58, just applying the log base a rule that we learned. 59, involving the arc trig rule that we learned. That was on the last quiz that we did.
Mr. Yang, can we go over 59?
Yeah, 59.
Yeah.
I like to think of x over 2 as 1/2 x. Okay, same thing. Okay, so the rule that we're going to apply is the derivative of arc tangent of u is u prime over 1 plus u squared. So our u value is right here inside the parentheses. Okay, so we're just going to do what the rule tells us to do. U prime, so the derivative of 1/2 x is just 1/2. All over 1 plus u squared. So I'm going to square both the x and the 2. So here's our derivative, but it doesn't match any of the answer choices initially. So we're going to find a way to collapse these complex fractions here. So one thing I see is I can maybe try to get this a little cleaner, maybe get this down to a common denominator so I can get it down to one fraction. So my common denominator is going to be 4, right? Because right now it's sitting at 1 over 1. I need to balance my fraction. 1 times 4 is 4. This one is okay. It's already 4. So let me rewrite the problem here. I have 1/2 all over 4 plus x squared over 4. Okay, we still have a complex fraction, but at least we've gotten this a little bit cleaned up. All right, we got this down to one fraction. So now if I want to collapse these two together, I can think of this is a fraction in the denominator. What if I push this fraction up to the same level as the 1/2? and then I can see what cancels out or combines. But anytime I want to move something above or below, I got to do the reciprocal, right? So I'm going to multiply the top and bottom by the reciprocal. So this completely moves because it cancels out up to this point here. And now we have 1/2 times 4 over 4 plus x squared. The nice thing about multiplication and division is that if I see any matching pairs, I can start to cancel things out. So that leaves me with 2 over 4 plus x squared. E. Questions with 59. And then finally, number 60 is finding the derivative of inverse at a point. Yeah, let's do this one here. So this problem tells us that f and g are inverses of each other. Okay. And I like to go through this chart because this chart kind of helps me map my progress around my function and inverses, derivative and order pairs. So I'm trying to find g prime of -11. So that's my ultimate goal. Okay. But they tell us that g of -11 is -3. Now we're talking about f and g, right? They're telling us that f and g are inverses of each other. So if that is truly the case, then I know that there is some variation of this order pair that's going to exist on the f graph. And that variation is where my x and y values will be flipped. If this is truly an inverse function, then this will always be true. Okay, are we good with that leap here? So after this, it actually gets a little bit easier because really, if I can find the slope of the f graph at -3, and we can do it because we have something available for us to find the derivative and evaluate it, then the slope that we find is directly related to the slope that we're trying to look for. And these slopes will always be reciprocals of each other. Okay, so if this is 2/3, then this will be 3/2. If this is 8, then this will be 1/8. So really, all of our work is just trying to figure what this value is. This is the part we have to do the calculation, but then after that, we just have to be able to make the connection that these slopes will always be reciprocals. Okay. So let's work towards finding f prime of x, and then we can plug in a -3. Okay, so let me distribute that 1/27 through. Maybe it's a little bit easier to think about it from that perspective. Okay, so I'm going to find f prime, and then I'm going to work in the -3. Plug the -3 in for x. I may need to use a calculator here. So it comes out clean to be just a whole number here. So I found the slope using on the f side of things. So if my slope is 17, then the slope of my g graph at -11 must be what?
-3.
Not -3. It's g prime, the g prime. So the slope is going to be related to this number here.
Would it be 1/17?
There we go, 1/17. So between the function and inverse, at the function level, their order pairs will be flip-flopped, but at the derivative level, their slopes will be reciprocals of each other. All right, any other problems that I may have just briefly skimmed over that you want to see worked out?
Could we maybe do 55?
Okay. Yeah, that's a good one. We have a pretty messy log problem, right? There's only one log expression, but that's a really big U value that we would prefer not to find the derivative at this point in time. So we want to try to break this into smaller parts. Numerator and denominator can be split up into addition and subtractions between logs. And just understand that the denominator are always going to be part of the negative log. So I'm looking at three things here. I'm looking at this term, and this term, and I'm going to separate them into each into their own individual natural log term. So I have the numerator here. Anything in the denominator is going to be preceded by a minus sign. Okay, how does that look to you? This is not the derivative yet. We're just breaking this into easier parts. Good so far. I can do a little bit more work with that square root. That square root can be rewritten as to the 1/2, and eventually that 1/2 can come down in front. So we can go a little further. Before we do the derivative, if we bring those exponents in front, things will be a lot easier with our derivative step. So that's power property. So now everything is nicely cleaned up. All of our u values are relatively easy to work with. So now we can apply our derivative rule. So our derivative that we're applying is the fact that natural log of u is just u prime over u. Okay, so just going to apply u prime over u for every term, and then any coefficient is just going to hang out in front. And u prime over u. U prime over u. And then u prime over u. Maybe I can do a little cleanup here. The 2's can cancel out. I can multiply the 2 and the 6 together. Get D as my answer choice. Okay, anything else? All right, so on Monday, I will do packet, I'll pick problems from packet 2, 7:30 and 3:30, morning and afternoon. Okay?
Thank you, Mr. Yang. Have a nice weekend.
Yeah, have a great weekend. See you, Joey. Bye,
Thank
Ishida.
you, Mr. Yang.
Bye, have a good weekend.